I guess we can move on to Wasserstein GAN. Again, you're working on the loss function and your divergences. Wasserstein GAN is another divergence. The video is online, so I'm not going to spend too much time. As for the overview, what are we doing? If in the perfect scenario, you can parameterize the underlying distribution, like what we are able to do for text using the softmax function, then you would just go ahead and use your maximum likelihood estimation to train your neural network. And that one is actually equivalent to KL divergence between the real data and the distribution of the real data and distribution of the model. So even maximum likelihood, you are minimizing a distance. You're minimizing a KL divergence. Let's approach the problem of a generative process from the perspective of choosing a divergence, a distance. Somebody might say, go ahead and use your total variation distance. Somebody might say, use KL divergence. Somebody might say, use Jensen-Shannon divergence. And this is actually the original GANs. Somebody might say, use Pearson chi-squared. And that's going to give you least squares GANs. And somebody might say, use Wasserstein distance. And if you use Wasserstein distance, similar to the same principle that computing KL divergence was not practical, computing Jensen-Shannon divergence was not practical because you don't know the functional form of your distribution. In a similar fashion, computing the Earth mover distance is not practical. But what is practical is using a theorem that's going to give you an objective function to work with. And this time, you're going to use a neural network. So you're going to be seeking help from a neural network to train your generator. And that one, assuming that your neural networks, you can control them so that they have a Lipschitz norm of 1, then you're going to end up with an objective function that is equivalent to minimizing the Earth mover distance. And whenever you have a function, you're going to put a neural network on it, or it's a good idea to put a neural network on it. And this is the objective function that you're going to be calling up. You have your generator, and this guy, you can call it your critic, and your critic is going to look at real images and fake images. And something nice about this objective function is that unlike Jensen-Shannon divergence, this actually has a meaning. As it goes down throughout the training process, there is going to be a strong correlation with higher and higher quality images. Unlike the objective function that you had for regular GAN. That one is doing something, it's up, jumping up and down, but then you don't know, are the quality of generating images getting better or is it getting worse? So think of it this way. You sit behind your computer, you code up your ideas, and then the only signal that you have to see whether you should spend 1 week looking at your objective function is whether something is actually going down or is it going up. With GANs, the original one, you're going to be staring at your screen, and then some numbers are going to show up, and then it is very hard to interpret them. And that's the difference between these two objective functions. And there is only a catch here. You need to put some structure on your neural network to be Lipschitz. And be Lipschitz continuous with some constant, the constant being 1. And there is an ad hoc method in the paper, which is clamp the weights. If any weight of your neural network during training is going to escape a box, clamp it into the box, force it to be inside the box. And that way you can sort of make sure that these functions, these neural networks are Lipschitz continuous with some constant. It's not going to end up being 1. You cannot control it. And in the next few sessions, we are actually going to try to control this Lipschitz continuity property. Intuitively speaking, why does this framework work and why does a regular GAN suffer is if this is your generated data, this is your real data, you want to take this distribution and shift it to the right. This is the entire role of training, and keep generating samples that are here. If you use your usual GAN discriminator and your discriminator ends up being really good at some point in your training, this is going to associate a probability of 1 to these, that these are definitely generated. and these are definitely fake, or these are definitely fake, these are definitely real, or the other way around. It means that there is going to be not much learning signal going on. These are constant functions. The derivative of a constant is 0. So there is not going to be any learning going on. The critic is going to look something like this for this simple problem. And there's going to be learning everywhere. There's going to be gradients. So this function has gradients. The other function has 0 as its gradients. And that's why perhaps Wasserstein GAN is a better objective function for training your generative adversarial networks or generative networks. Any questions about Wasserstein GAN? Is everything clear? Okay, perfect.